Let's talk about electrons, light, and then later on we will talk about electron clouds. So because we're using light to help us discover the properties and characteristics of an electron, let's look at the properties of a wave. So on this diagram down below, we see that a wavelength is from crest to crest. So some wavelengths are very, very long. Some wavelengths of light are very long. Some are very, very short. The frequency would be if you were standing right here and the waves were coming at you. If you were to count how many crests go by, that would be known as the frequency. And then last, we can look at the speed, and the speed of light is a constant. It is given the letter c, and we're not going to be making any calculations, but those are just, if you're interested, some of the units that are used in frequency, wavelength, and speed, and also the quantities. We can look at a formula to help us see the relationship between wavelength and frequency, but we're not going to be doing any math calculations. I like formulas though because they help give me a sense of the relationship. So I know that if anytime I have light, it's always going to be moving at the speed of light. So that means this value is always going to be the same number. So therefore, if I have a very long wavelength, I will know that that frequency has to be a small number because I have to multiply these numbers to get that speed of light, 3 times 10 to the 8th meters per second. And as a reverse, if let's say I have a very short wavelength, that means that this frequency has to be large because again, I have to end up with the same number. So this is an inverse relationship. And that means that if my wavelength goes up, that means my frequency will go down, and vice versa. If my wavelength goes down, then that means my frequency will go up. So inverse means that, again, if one goes up, the other one goes down. So let's look at this chart. This shows the whole electromagnetic spectrum. And there is a video I do want you to watch about this, and it should be in with your notes. It's a film put out by NASA. But we see that as far as the electromagnetic spectrum goes, we have radio waves all the way to gamma rays. And so we can see the wavelength. So again, the wavelength is this funny looking backwards H. And we also have the frequency, and the frequency is a V, or sometimes in physics they'll have it like a little cursive F. But we can see that radio waves have a very, very long wavelength. And as a result, that means that the frequency is short or a small number. And we can look at over gamma rays. And so because it's such a short wavelength, then the frequency is quite high. You can see that it's 10 to the 20 versus radio waves, which is 10 to the 4th. As far as our eyes go, our human eyes, we can only see a very, very small portion of the electromagnetic spectrum, and that is visible light. And you can see that it's spread out here. We have red over here, and we have violet. And a good way to remember the visible light spectrum would be Roy G. Biv. So we have everything from red all the way to violet. So red, orange, yellow, green, blue, indigo, violet. And so our eyes can only see those particular wavelengths. So looking at this chart, we know that an inverse relationship would be the wavelength and the frequency, meaning that if the wavelength goes up, the frequency goes down. We can also look at the energy, and we can see over here that we have high energy on this side, and we have very low energy over here. And how I remember this is radio waves aren't likely to kill me, but gamma rays, they will kill me. Gamma radiation is emitted in a lot of nuclear processes. So if you've ever heard of nuclear poisoning, that's from the gamma radiation. So, and it's because very, very high energy wavelengths. All right, so looking at this chart, we can look at a direct relationship, and we can see that if our frequency goes up, so does our energy. And so because of that, this is a direct relationship. So As frequency goes up, energy goes up, and as frequency goes down, energy goes down. We also can go back to the inverse relationship and then put energy in with it. So you can see that as my wavelength goes up, then my energy will go down. So they're all kind of related to each other. So you should be able to know the electromagnetic spectrum, know where radio waves land and where gamma rays land. And what about those microwaves? So our cell phones work on microwaves. Is that a high energy frequency? Looking at the chart, we can see that microwaves just have a little bit more energy than radio waves. Here's another chart that shows the visible light spectrum. So you can see it's just a very, very small wavelength that we can see. And looking at this, we see that red has the longest wavelength, so therefore it will have the least amount of energy. So we see that as far as the energy goes, it's increasing as we go up towards the violet. Violet has the most amount of energy, red has the least. So we can apply this to good old science fiction, Star Wars. So we have a red lightsaber and we have a bluish lightsaber. Which one would have more energy? We find out that the blue would. So you would think that the blue would be the winner of this battle, but spoiler alert, the red actually wins. All right, so let's apply this information to chemistry. So in 1900, Max Planck, the German government approached him and asked him to build a better light bulb. Light bulbs at the time, they gave out a lot of heat, and the German government didn't want to spend all their money on light bulbs that were just going to burn up really quickly. So they wanted a light bulb that put out the energy in light and not heat. And so they had Max Planck study this. He studied black body radiation, and he described energy as little packets of wavelength. And he said each of these little packets could be different colors. So we could have some packets that have violet, and then we should have some packets of energy have red. And he called these little packets of energy quantum or photons. So it's a little packet of energy. There is an energy equation, and we kind of alluded to on a previous slide that energy and frequency have a direct relationship. Planck discovered that all his calculations were off by just a tiny, tiny amount, and he didn't know what to do with this, and so he told the scientific community, see if you can see what my mistake is. And the scientific community said, no, Max, you have discovered something new. And so this little tiny amount that his calculations were off is now known as Planck's constant. It's a really, really small amount, but we see that Planck's constant times the frequency will give us a calculated energy in joules. Einstein looked at Planck's results. He also considered light to be these little quantum, and Einstein got the Nobel Prize for the photoelectric effect, which is right here. It just means that he took light and he shined it on some metal, and when the little photons of light hit the metal, then electrons were able to move. Let's look at light when we put it through a prism. Now, all light travels at the speed of light. When you put it through a prism, because the diffraction is a little bit different depending on the color that you have, you're able to actually see all the wavelengths that are in that white light, because white light will emit all the wavelengths of light. If we take light through a prism, we get this little rainbow. If we take that light and shine it on an element, so a particular type of an atom, we get that the atom will absorb some of those wavelengths of light, and then as soon as it absorbs it, it will immediately emit those wavelengths of light. So you can see here it is absorbing particular wavelengths. So if I were to shine a yellow light on this particular element, you would see that nothing would happen because it doesn't absorb yellow, and you can see it doesn't emit yellow. So that would be a total non-reaction. However, I could shine this particular wavelength of green. You can see that it would absorb it first and then emit it. So how does this all happen? So down here at the bottom, we have our elemental sample. So these are our atoms that happen to be in there. And we can excite these atoms of this particular element by passing electricity through it or shining light on it. And we can get an absorption spectrum and then an emission spectrum. So in this emission spectrum, we can see for this element, violet, blue, violet, green, and red are the particular wavelengths that it would absorb and then emit. And it depends on what element you have with what emission spectrum you'll get. And so these act kind of like fingerprints. So if you didn't know the identification of a sample of gas, you could shine a light through it or a current of electricity, excite those electrons, and you could get these elemental emission spectrum. So you see this top one is hydrogen. So when we look at hydrogen, it has kind of a bluish color, and that's because there's so many wavelengths down here. So my eye would see blue. Sodium has a very brilliant yellow color, and that's because this is the only color that it will absorb and then emit. This next one is helium. So helium has also bluish colors, and then neon, like in neon signs. Why are they so orangey red? And that's because its elemental emissions spectrum, it will absorb and then release these red, orange, yellow wavelengths of light. And last but not least, we have mercury, which is found in a lot of fluorescent lighting. And so you can see that it has this range between yellow and purple. So why this is important: if I have an unknown sample, I might get a mixture, something that looks like this, and I can compare the different elements and I can see what's in here. When you identify what's in your sample, you should have all the lines of all the elements. So for hydrogen, I would want to make sure that it has this wavelength, this one, and these. Some of these are a little dark for my eyes to see, but you should be able to see that they appear in the sample, and they should be exactly in the same place. If you have one that's missing, then it's not in the sample, so you need to have all of them. So you can see in this sample I have hydrogen, carbon, and oxygen because all those wavelengths I can match up. So this one's in black and white. Go ahead and stop the tape and see if you can figure out what is in the mixture here at the bottom. So can you figure out what's in it? Can you figure out what's not in it? So stop the tape and see if you can figure it out. Okay, we're back. So again, when you look at this, you just want to make sure that in the sample, an element will be in the sample if all the wavelengths match up. So one, and having a ruler would be very helpful, but one I can see that doesn't appear is this one right here. It's kind of hard to draw straight on my screen, but you can see that it's not argon because it's missing that one wavelength. So again, if one is missing, then it's not that. I can see that also for barium. It's not barium because you see how that wavelength is missing. So I know it's not barium. But you can go through and you can line everything up. It looks like all the ones for calcium are there. So I would say yes, calcium is in that sample. So you can go through each one of these and decide if it is in the sample or it's not in the sample. So this is important when we want to identify what kind of elements are out there in the universe. So when we look at a particular star out there far away, we can use these elemental fingerprints to figure out, is there water on Mars? Is there oxygen on a certain planet? Because it will give off the elemental fingerprint of water or oxygen. So even like clusters far away, these gas clusters, we can figure out if there's carbon in there or if there's nitrogen or if there's oxygen, and we can see if distant galaxies might have the potential to support life. So what is going on in the atom that is causing the absorbing and emitting of light? And then why is each element different? So why do I get a different fingerprint for helium than for hydrogen? I mean, they're right next to each other on the periodic table, just a difference of one proton and one electron. So why did it have such different elemental signatures? So this model is called the Bohr model. So Niels Bohr is the one that thought of this, and he imagined electrons orbiting the nucleus. We don't believe that anymore, but this does explain these elemental fingerprints. So when electrons get excited, they jump from their ground state or their lowest energy state to higher energy orbitals. And these higher energy orbitals are represented by rungs or orbits around the nucleus here in this Bohr model. So when they jump up to a higher energy level, they don't stay there forever. They're immediately going to drop back down. And when they drop back down, they can drop back down step by step to the ground state or all at once. And if they jump all at once, they will have a higher energy wavelength emitted. So jumping all at once, maybe you get a purple light. If you go step by step, maybe you get a red light, a red wavelength. From this, Niels Bohr was able to come up with a model of what's happened with the electron. We know the electron's not in the nucleus, but what is it doing? The Bohr model says that the electrons are going around like planets around the sun. They're going around in orbits around the nucleus. We don't see this orbital theory or the Bohr model being true anymore. There's another model that we use now. But this does explain what is happening with these elemental fingerprints, that the electrons are absorbing energy and going further away from the nucleus to a higher energy level. And then after they absorb it, they release it. They can release it all at once and have large quantum jumps, or they can do a step-by-step quantum jump. So this just summarized the Bohr model, or the planetary model. Electrons travel in definite circular paths called orbits. Now we are correcting that and we call them orbitals. And we'll talk about it in just a minute. It's more of a probability cloud. The electrons have fixed energies called energy levels or shells, and that is correct. If we look at the periodic table, we see these energy levels by the rows 1, 2, 3, 4, 5, 6, 7. But those are the energy levels or shells. You can see that the rungs of the ladder, their space kind of far apart at first, and then they get closer together. As you see the energy increasing, you see those energy orbitals becoming a little bit closer together as far as their probabilities. So the amount of energy required to move an electron to another energy level is called the quantum. So if you've ever heard the term quantum jump, then these are electrons that are absorbing and going to higher energy orbitals, and then when they fall back down to their ground state, they release that energy in the form of a wavelength. The excited state, that means they're further away from the nucleus. The ground state means that they're at their normal energy level, the lowest energy level they can be for that particular electron. When they absorb the energy, again, they don't hold on to it forever. They will, after they absorb it, release it, and they will release it step by step, kind of all at once, or with a larger quantum jump, then you get a larger frequency of light or a shorter wavelength. Electrons, we don't find them in between levels. We only find them in these energy shells. And later on, we're going to talk about how these electrons can be transferred from atom to atom. But here we're talking about how they're moving from one energy level to another. So again, my electron in the ground state, it can absorb some energy, go up to an excited state, and then it can release that energy all at once. If it does that, you're going to see a shorter wavelength of light. If it releases it step by step, then you're going to see a longer wavelength of light emitted. As I said before, the Bohr model is incorrect. It only worked with hydrogen, but the time you added one more proton and one more electron, and we're looking at helium, and then one more of each and looked at lithium, the math didn't work out. And so something else was going on, but we still look at Bohr's energy levels and different distances around the electron. So that is what's good about the Bohr model, plus it's easy to draw. But scientists, having Bohr's model fail, they revisited what an electron really is. Is an electron this little particle of energy, or is it a wave? And today I would tell you electrons are waves, which is a little bit different and a little bit hard to wrap your brain around. So a scientist by the name of Schrodinger, he looked at the wave nature of an electron, and he did this really complicated wave equation. And there it is. But I do want to point out that, do you see this X, Y, and Z? So what he did was he plotted the probability of finding that electron in any one place around the nucleus in space, so a 3D model. And he came up with something that looks like this. So this is a 3D model of the electron probability cloud of hydrogen or helium. Hydrogen only has one electron, so you can see that at this distance right here, this energy level, that's the highest probability of where you would find that electron for hydrogen. You can graph it like this. So there's a 90% probability of finding at 53 picometers away from the nucleus. So these are those energy levels that Bohr was talking about, but now Schrodinger, he called it an orbital, and he called it a probability cloud. And he called it a probability cloud because, do you see all the little dots out here? So there is a possibility that you would see the electron a little bit further, or a little bit closer to the nucleus. But again, a 90% probability that you'd find it at that particular energy level, or this 53 picometers for hydrogen. If this was helium, I would just add one more electron into that probability cloud. It's going to look the same. So in a probability cloud, you can have one or two electrons. So that's why this can represent hydrogen or helium. So doing his big, complicated wave probability equation, he was able to find the probability of where you would find each electron, and this is how we see the atom today. So this is called the wave mechanical view of the atom. It's also called quantum mechanics, and I think the name is more complicated than the explanation. So again, electrons are in probability clouds around the nucleus. Some of them are spherical. So this is an S cloud. So if you've done electron configuration, this is what an S electron would look like, and these are P clouds. And you can see the P cloud is kind of a dumbbell shape. So running it through that math equation, that probability equation, you actually get the most dense probability of where you would find those P electrons on the x-axis, the y-axis, or the z-axis. So these little dumbbells. So again, probability clouds don't have to be spherical. Here's some different shaped probability clouds. These are the d orbitals. So for your transition elements that have d electrons. And there's your f orbitals. So that would be like your elements that have more electrons. So like your actinides and your lanthanides. And here's just kind of a summary of all these probability clouds. So you have S, P, D, and F. You don't have to draw them or really know about them. Just know that the atom is very, very complicated, and you can get different shape probability clouds. Here's just a picture that shows what an atom might look like. If you were able to see an atom with the naked eye without these high-tech microscopes, it would appear as a blurry cloud. So if you've ever wanted to know that, that's what it would look like. So this is optional if you watch this, but if you're interested in what the atom looks like, this quantum mechanical view, I'm going to be using the electron configuration to help show what the atom might look like. So let's start with hydrogen. So hydrogen electron configuration is 1s1. So that means that I have a probability, and I'm going to draw dots here just to begin with to show that it is a probability and it is 3D. But it's kind of difficult, so I'm just going to use a solid line. But no, it's not a solid line. It's a fuzzy line. So it kind of goes up, it kind of goes a little bit in, a little bit out, but 90% probability of finding that electron at that distance from the nucleus. So that's what hydrogen would look like. So as far as its electron cloud. So helium, again, it's first energy level, and I have 2 electrons. It's going to look the same. I'm just going to add one more electron, and there you are. Let's go on to lithium. So lithium has everything hydrogen and helium have, and it also has an electron in the second energy level. So that 2 tells me it's just further out from the nucleus. So again, this is a fuzzy line. But again, it's hard to draw on my computer here. So this is a spherical. The electrons can be in and out, but this is what lithium would look like. The next one, beryllium. Beryllium has everything lithium has, plus one more electron, so it's going to look the same. So let's come to boron. Boron has 5 electrons, so it has everything helium and hydrogen, helium have, lithium, beryllium. Plus it has its own. Now we're getting into the P clouds. So remember, they don't always have to be spherical. So I'm just going to draw the dumbbell, and it comes out to the second energy level, and I just have 1 electron in there. And again, it's not a solid line, it's a fuzzy line. After boron, we have carbon. Now for the p orbitals, because there's 3 of them, the electrons do something a little bit different here. So instead of sharing in this first p orbital, the second electron is going to be in its own. So all of the p clouds have the same energy, and so the electrons tend to spread out. So you're going to put 1 in the x orbital, then 1 in the y orbital, then 1 in the z orbital. And that x, y, and z, scientists really don't know the order, but just that they go in their own orbital. So after carbon is nitrogen. So we have 1s2, 2s2, 2p3. So this is going to be the orbital that's coming straight off the screen. And so that I have basically a px, py, and pz. Okay, so for the rest of the elements, the 2p elements there, so we have oxygen, fluorine, and nitrogen. Then what they would do is they would go back and they would, so first put an electron in the X, Y, and Z, and then they go in and they put a second electron in the X, Y, and Z. So by the time you got to neon, you would have these orbitals. By the time you got to neon, you would have 2 electrons in each of the orbitals. So that would be totally filled. All right, and then by the time we got to magnesium, magnesium would have everything that neon has plus 1 more electron. So 1s2, 2s2, 2p6. So all that would be filled in, and then it would have 1 electron in that s electron. And again, it's not a solid line, it's a dotted line, and it's spherical if it's an s electron, and dumbbell shaped if it's a p electron. But this is the quantum mechanical view of the atom. So we have protons and neutrons in the nucleus, and we have electrons outside the nucleus. They're found in different energy levels, and we can see these energy levels. So we have energy level 1, 2, and 3. So 3 energy levels I've drawn so far in this quantum mechanical model, and I think it's quite pretty. So chemistry is pretty, but this is how we see the atom today, and we see that there's these different energy levels because of light that is emitted when electrons are excited and then when they emit that energy.